Anyways, partial fractions for this is, first think way back into pre-calculus, we would take this big expression right here. Now, if I had to integrate this, I'd like to think we could. If I were to just, we're not actually going to right now, but if I were to integrate that, what would you use for integrations on those? Natural logs, right? So we're all good there. So if we can get to there, we're good, right? Well, what happens if I wanted to combine this, if I wanted to group those two together? What would you need? You need a common denominator, right? So the common denominator would be x minus 2, and then it would be x plus 3. We're going to go through this kind of fast. And then to do that, this one over here would need an x plus 3 on the top and the bottom. You multiply that by 1, so that would be 1x plus 3. And then this one would need an x minus 2, and you're multiplying that by this, so it's going to be x minus 2. And then when you add all your like terms together, let's see, you get 1x here minus an x, so your x's cancel. And then you get 3 and a negative 2, so positive 2, so you get 5. So we get 5 over x minus 2, x plus 3. Pretty quick, pretty easy, not a big deal. You guys are all good with that, I hope. Okay. Now what happens if I said integrate that, though? Or integrate x squared, if you FOIL that out, let's say the denominator was x squared plus x minus 6. Is that on the denominator? Right. That's tough to integrate something like this, right? And so what we have to do today is unfraction this guy. We have to take this guy right here, and we have to split it up. We have to split it up into what they call partial fractions. So we're going to take this one big fraction right here and try to separate it like so. Okay. Now we've separated fractions before, but most of the fraction separations that we've done have looked like this. They've been like 5x plus 1 over x, and we can separate that into 5x over x plus 1 over x. That hasn't really been a big deal. Okay, if you got the numerator right there, we can cut that out. So, anyways, that's one split fraction right there. We've done stuff like that as well, but it's a little tougher when the denominator's got some multiplication in it. So there's some tricks for how you do that. And so today that's what we're going to do is we're going to split up a fraction using partial fractions. Because if we can get it to here, we can integrate and like this. Okay. So actually, no new integration techniques as far as that goes. Just one little extra way to do it. So anyways, let's say we want to integrate 1 over... So anyways, the first step, there's a couple processes, there's a couple steps to make this work. The first thing is you want to get multiplication on the bottom. If you can get multiplication on the bottom, you can see as the common denominator would be split up. You can see what partial fractions there would be in your denominator. So you would split this up first. This was split up to x, what's this going to be, x minus 6, x plus 1?
X minus 2, x minus 3.
X minus 2, x minus 3?
Yeah.
Yeah, it looks better. Cool. Okay, so that's the first factor. Now, as far as the split goes for this, we have 1 divided by x squared minus 5x plus 6 equals. Now, these are going to be my two denominators. Okay, I want two separate fractions here. I want this plus another fraction. Now, those are going to be my two separate fractions right there, x minus 2 and then x minus 3. So I'll put an x minus 2 on this one and an x minus 3 on that one. Now, all we have to do is figure out what the numerators are, and then we're good. Okay, and then that's it. That's all there will be to it. Now, we don't know what they are, but we do know they're just going to be constants for this one right here. So we're going to say a and b. It gets a little trickier than a and b a little later, and I'll show you kind of how those work. But for now, if it's just going to be a regular x plus 2, x minus 3, x plus a number, x minus a number, it's going to be an a or a b. Okay, or if it's just an x. But anyway, so a and b. Now what I have to do is I have to try to solve for a and b on this equation right here. Okay. Now it's a little tricky, but let's say you multiplied everything by the common denominator. The common denominator is this right here. So if I multiplied everything by that, right here, if I multiply by the common denominator, all that's left is 1. So I'd have 1 equals. Over here, if I multiply by this common denominator right here, I'd be left with a times x minus 3. So I'd have a times x minus 3. Plus, multiply this by the common denominator, which is basically both of them. The x minus 3 cancels. I'm left with b and then x minus 2. So b and then x minus 2. Okay, so that's like one statement that works. It's an equation. It should work for every x because our original one is going to work for every x, and I haven't done anything illegal. So now I got to find out what a and b are. What you can do is you can pick any value for x that you want. It's a little bit of freedom, right? Well, there's some obvious ones to pick, I would think. Like, let's say you wanted this term right here to go away. What would you plug in for x? 2, right? So if you plug in a 2 for x, that makes 2. That would make this part right here 0, and it makes that whole thing go away. So now I'm left with 1 equals a. I'm plugging in a 2 for x, 2 minus 3, and then now I can solve for a. Okay, so I get negative 1 here, so I get 1 equals negative a, so that means a would equal a negative 1. Okay, so we solved for a. That's good. So now my top equation right here, I've just solved for it. I've solved for a equals negative 1. Now I've got to find out what b is, so what's your obvious choice on this one to plug in? A 3, right? Because you want this term to go away if you can. Okay, so if I plugged in a 3 right there, that term would go away. So I would have 1 equals, this term goes away when I plug in a 3. I've got b, 3 minus 2. And so I get 1 right there, 1b equals b, so I get b equals 1. So I get b equals 1. Okay, so that's how you split it up. That's what they call partial fractions. Just split that up. Now to integrate that, integrating it isn't too bad. If I integrate this big mess right here, just using natural logs for all of that. So this one would be a negative natural log of x minus 2. And then plus looks like the natural log of x minus 3. And they might condense that together. If it was free response, I'd just leave it like that, no further simplification. It's really good.
So what if you plugged in like 100 and it never canceled one besides that?
Then you're bad at picking numbers.
Okay.
You could actually, if you really wanted to, what you could do to make this like way harder than it really needs to be, you could plug in anything you want for x. If I plugged in 100, right, for x, I would get some equation with a and b, right? If I plugged in negative 100, let's say, I would get a second equation with a and b. And then you can do substitution or elimination to solve for a and b. Which on some you have to do that. I'll show you one where you have to do that. But anyways, you're right. It's not always going to cancel out super nicely. This was just to get the ball rolling on some of it. So,
can you explain again why that a times x minus 3 plus b?
Oh yeah, I kind of jumped a big step there.
Why does it equal 1?
Because if I multiply everything by x minus 2, x minus 3, if I go right here, x minus 2, x minus 3. Here I go x minus 2, x minus 3. Here x minus 2, and then x minus 3, right? And this was a, and this was b. Right? And so here, x minus 2, x minus 3 is that. Those two are the same. So these two, they cancel each other out, so all I'm left with is 1.
Okay.
Here, I cancel out an x minus 2, I'm left with a times x minus 3. Here, I cancel out an x minus 3, so I'm left with a b x minus 2.
Oh, okay.
Okay? So I'm always multiply that by that common denominator. You're always going to do that. That step is always the same throughout, no matter what kind of problem we're going to do. So, anyways, that sets up like this basic equation so that stuff can cancel out for us, so stuff goes away. Anyways, all right. So yeah, that's the start of it. Let's go a little harder. Step it up a little bit. One with let's do one with a quadratic, huh? Or is that one too hard? No, we can do it. We can do it. All right, there are a couple tricks, obviously, to doing this. A couple exceptions, as there always are. So let's do.
Oh my goodness, that was really
Now, sometimes it works out a couple little things just to kind of look for. Sometimes the exponent on top might be a little bigger, and in that case, you would probably long divide first. There's other cases where, you know, this function right here, the derivative of it might be just smiling at you on the top, and so you might just be able to jump straight to a natural log. So just maybe watch out for some of those little tiny shortcuts. You might be able to factor the top and the bottom, and something cancels on both of them and makes it a little easier. So just little things to look for as you're going through these problems. But for the most part tonight, they're going to be all pretty straightforward. There's three types of these problems that we're going to be doing. First one is a pretty basic one like the one we just did. This one is actually going to have what they call a repeated factor, and I'll show you what that looks like. If I were to factor this denominator, you would take an x out first, and then you're left with x squared plus 2x, and then plus 1. And then when you factor that, you got x. This is going to be x plus 1, so it's going to be x plus 1 squared. Now, when you have a repeated factor like that, it changes just a little bit. You have to be a little bit cautious on how this is going to go. As far as your denominators are going to go, you're going to have the same equation, 5x squared plus 20x plus 6. Divide that by the x to the third plus 2x squared plus x. And now when you split this up, as far as your denominators go, that's the first thing you want to look for, is what are my denominators going to be for this one. Now technically I have three factors here. I've got this x right here. I've got this x plus 1 is one of my factors, but this one happens twice. They call that a repeated factor, and when this happens, you have to do something a little extra on this one. So just a quick heads up. The first factor is x, so that's going to be an x there. The next factor is really an x plus 1. Pretend that squared isn't even there. So the next one is going to be an x plus 1. And then the next one is going to be the x plus 1, but we're going to square it. So we're going to take x plus 1 and then square that guy. So when we have something repeated to a power, you have to build up that power all the way throughout it. Okay, so if this was x to the 20th power, let's just say, if that was x to the 20th power, you'd have to have x plus 1 squared, x plus 1 cubed, x plus 1 to the 4th, x plus 1 to the 5th, to the 6th, the 7th.
Is that like when you factor a cubed?
It's like when you factor a cubed, exactly. You're exactly right. Okay. Now, if you hadn't put that there, if you hadn't put that squared there, if you had just said, all right, well, if I split those fractions at x plus 1s, and this was just a regular thing, you could just add those together and put a 2 in front of it and call it good. But unfortunately, it doesn't work like that with the powers. So, anyways, so we have to worry about that little square right there. Got to throw that in there. Still have our A, B's, and C's that we're solving for, A, B, and C. Still have to solve for those somehow. So we'll just take a look at it, see if we can't figure it out. So first thing I would do is multiply by the common denominator, which is this guy right here. Now this is going to cancel on that side, so you're always going to be left with the numerator over here. 5x squared plus 20x plus 6. That doesn't change. This part's a little tricky. You're going to multiply everything by, maybe I'll leave it in its factor form. Multiply everything by an x plus 1 squared. That's what you're going to multiply everything on that side by. x plus 1 squared, by everything. Now stuff cancels great. Like here an x cancels, so you're going to be left with a x plus 1 squared. Plus, now here one of the x plus 1's cancels, so you're left with a b. You still have an x and then one x plus 1. So it's going to be x plus 1. Plus the last term, an x plus 1 squared cancel out of both of those, and so you're left with a c and an x. So you're left with a c and an x.
I'm getting confused using C for like constant.
Yeah, it's kind of weird. You can skip it and use d if you want.
ABD.
It's fine for me.
Yeah, DX.
Dx would be a lot worse. Actually, that could happen if your quadratic term is the third term.
This is not doing
Yeah.
Fourth term, but it's a capital D, so that's a little better. Although actually, one of the notations way back in the day was D with a little x like that was one way to say derivative. Anyways,
Back in the day.
back in the day. All right, now this one's going to be a smidge more challenging, a little bit more challenging, tiny bit. Let's see if we can't figure it out. First thing, try to pick some obvious terms to plug in to hopefully make stuff go away, I hope. Like, what would you guys plug in first? Negative 1's a decent idea, but I would plug in 0. 0 is a better one to start with. Just for the first one, because it's going to be easier, right? It's going to, and this side's going to be way easier to figure out, right? Because if you plug in a 0, what's left over here? 6, right? So you have 6 equal, this is when x equals 0. Let me write it this way. When x equals 0, I get 6 on this side equals, well, if it's 0 here, 0 plus 1 is 1 squared, so I get a. So I get a is 6 for that. Plus, now if I plus, let's see, x is 0, right? So 0 times who cares is going to be 0. Plus c times 0 is still going to be nothing, right? So we have a equals 6 already. Okay, so the first one's really quick, really nice. Now the second one, like you said, we have to plug in probably x equals negative 1. That would be my next pick. If I plugged in x equals negative 1, I'm going to be able to solve for c, looks like. Right, I've got a is 6. Now I should be able to solve for c with x equals negative 1. So plug in a negative 1. A little more work to do here. It's negative 1 squared. So this would be 5 minus 20, so negative 15. So negative 9. So I'm going to get negative 9 equals 0 and 0, and then c times what I said, negative 1. So I get a negative c, so that means c equals 9. Did a little bit of, you can do some of this stuff in your head because a lot of stuff cancels out, which is kind of nice. But let me write that up here. Okay, so we okay with that? Not too bad. Now we got to find out what b is. Now b is a little more challenging, a little trickier here, because there's nothing I can plug in that's going to make both of those terms go away. If I plug in a negative 1, it makes the b term go away. If I plug in a 0, it makes the b term go away. So I'm kind of screwed a little bit as far as picking either of the ones to make either of those go away. Okay, so this is why you save this one for last if you can. Well, now you can plug in whatever you want. It doesn't matter which value you pick. We already plugged in, let's see, 0. We plugged in -1. Let's plug in x equals 1 and see what we get. Okay, so now I'm going to plug in x equals 1. And let's see what we get. On this side right here, if I plug in a 1, let's say I get 5, I get 25, I get 31. So I get 31 on this side. Equals, now I'm plugging in a 1 right here. But we already know what a is, don't we? We already solved for that. So that makes that a little bit easier. If I plug in a 1, that's going to be 2. Squared is 4. 4 times 6, I'm going to get 24. So that first part is 24. Plus bx, I don't know what b is, so I'm going to leave b alone. B times, I know I'm plugging in a 1 for x, so this is going to be times 2, looks like. And then plus c, that I know c is 9. Times x, and x was 1 on this one. So now I can solve for b.
Wait, so why did you plug in 1?
I just arbitrarily picked it.
Okay.
It had nothing to do with it. Typically, because 1 is easier, so if you can pick 1 or -1, go for it. But if not, then I would have picked 2. I would just keep it small. You can plug in whatever you want. So. Or 100, if it so pleases you. So anyways, so anybody solve for b here?
It's like -1.
-1, cool. So we get -1.
Wait, why is the a value 24?
Why is that? The a value is 6, right? And I'm plugging in 1 for x. So if I go 1 squared is 2, 2 squared is 4. No, 1 plus 1 is 2. I said that wrong. 1 plus 1 is 2, and then 2 squared is 4, and then a was 6, so 4 and 6 is 12. So you get a little solving there, b equals -1, and you're good. So now you got a, b, and c. I guess I don't need to move it down. Now my a, b's, and c's are right here. I would just replace what a, b, and c are. And so my a I solved for was 6, my b I solved for was -1, and then my c I solved for was 9. Okay, integrate all of that big mess, and you're done. Okay, and then the nice part is most of these are natural logs. Most of these are really quick natural logs. Like this is 6 natural log of x. This is -1 natural log of x plus 1. This is not natural log. Right? Okay, you'd have to do u substitution on this one. Raise that to, put that at a -2 power up on the numerator. Bump it by 1, so that'd be the first power, and you're off the races. Okay? So, anyways. You can't use natural log substitution on this. You just use regular u substitution. U is x plus 1. It'd be u to the -2 if you moved it to the top. And then your du is 9. You just put that in front. So it'd be u to the negative first times the -1 in the front. So this would be -9 over x plus 1 is what it would turn out to be. So anyways, not a natural log though. So, all right, cool. So is that okay? It's a little tricky with this one was a repeated power. I just want to show you just a couple little things. Repeated power, x plus 1 squared. Then you have to do this repeated part right here. Okay? Okay. So far so good. Not it. We got to do quadratic versions too. We haven't seen any quadratic ones. So one last one, and then we're done.
So
And
we're
we're
doing
good.
like trigonometry.
We're only 20 minutes in. We're not doing trigonometry. We're
Oh, Jesus.
jumping over
The
that.
smiles over our souls.
Yeah, no. Not going to do that.
Trigonometry.
There's different ways to do the trig ones, I think. So
Okay.
you can use them with it, but
No,
it's not
we can't.
worth it. I don't think.
Goose goose.
Last one here.
Like, this is difficult looking.
This is quadratic key.
Quadratic. Duh.
Now the tricky part is you want to fully factor the denominator. That's kind of the starting for this. So you can take an x out of that first one. So it's x and then x minus 1 and then it's x squared plus 4. Now technically you can force factor this x squared plus 4. You'd end up getting imaginary numbers though. You'd have x plus or minus square root of 2i, or no, x plus or minus 2i multiplied by each other. It's a mess. So we don't want to go imaginary. So that's going to be considered to be fully factored. Okay, we can't take that any further. Although we do have a quadratic in here. Notice we have an x squared plus a number. That changes things just a little bit. It tweaks it. As far as my equations go, that's all going to stay the same. I'm going to have a 2x to the third minus 4x minus 8. And then divide that by the LCD. I'm going to cheat. Equals. Yep. And then we're going to split this up into my fractions. So my first fraction denominator is x. So I'll have an a over that. Plus second one, I'll have an x minus 1. I'll have a b over that. Yeah.
I like it.
And the last one's x squared plus 4. Now this one, since it's quadratic, it changes just a little bit. And there's the difference between this quadratic and the last one. I hate to say that. But this quadratic, the numerator, is actually going to be cx plus d. It's going to be a linear factor up on the top.
So if we just skip.
Because this right here, having that x squared, if you would end up doing common denominators between all of those, to get back to an x cubed, to get back to an x squared in my denominator for this part right here, this x squared goes to all of those, and I need an x factor on the top in order to get back to the top. But anyways, if you have an x squared plus 4 on the denominator, you always have to go to a cx plus d type problem. Okay, you're always going to have a linear factor on the top. Now the confusing part about that, I think the confusing part about that is this was x plus 1 squared. Technically that's quadratic, but we didn't have to do it on that one because the inside was just a regular x plus 1. And then we did like a repeated factor on that. Kyle?
What if it was like a non-factorable trinomial?
A non-factorable trinomial, there's going to be none of those.
But wait,
What if life throws us one?
There will be none of those.
okay, so
How about what if in order to save the world?
If it's a non-factored trinomial, then you're going to have to do a quadratic in the top.
You lose. You lose.
But it'd be ugly. It's going to be ugly. It's going to be gross. So it actually is not too bad. It's not too bad, but the A, B's, and C's are. You have to use a system of 3 equations to solve for your variables, which is kind of hard as far as these problems are concerned. So we're not going to do it. Anyways, we got to multiply by our common denominator here by our LCD. Okay, so I'm just going to cheat and write LCD right here. Save me a little bit of time. My numerator here stays the same. That's always the same. 2x to the third minus 4x minus 8. Equals here. Now when I multiply this by my LCD, I'm left with a, and then both of those terms right there. So kind of a big term here, x minus 1, and then x squared plus 4.
What? I'm not gonna have room for this.
I won't have room for it. I'll have to write another for it. I've already got a feeling. Wah.
Yeah, we should.
Not a crybaby. All right, then this one, let's see. We got plus b. We got an x and an x squared plus 4. And then plus, I'm out of room, cx plus d. And this is going to be an x minus 1.
Is CS plus D all mental like that?
Yep, yep.
Oh my goodness.
Donkey's going. Or donkey walk?
They haven't even got to the heart part yet. You guys are weighing hard.
I know we're going to get all of them.
Something makes at least 2 of them go away, which is good.
0.
0 is one of them. Yep, pick a 0. That's a good start. X equals 0. Okay, that's a good start. So here, let's say I get a negative 8 here. Equals, let's see, this term doesn't go away, but both of those terms go away with 0, right? Because there's an x floating around right here. X times whatever is going to be 0. There's an x floating around right here. X times whatever is going to equal 0. So the x0 makes both of those terms go away. So that means we just plug in a 0 right here. So we get a negative 1 and 4, so we get a negative 4, so we get negative 4a. So then a would equal 2. So that's not too bad so far. Okay, now we got to try to solve for a different one. So is there another one that might make some stuff go away? Yeah, positive 1. Yeah, x equals 1 would work. X equals 1 makes stuff go away, which is good. It actually makes this term right here, the a term, go away. It makes the cx plus d term go away, because it would make that 0 and then 0 times whatever. So all I'm left with is this term right here with a 1 plugged in, and I should be able to solve for that. A 1 plugged in on this side, by the way, would give me
A million.
negative 10, I think. That's what I think, negative 10. And then, let's see. Are you sure?
Yes.
Yeah. And then, let's see, that term went away. Here's a negative 1 plugged into here, so I've got, looks like b times a negative 1, so I'll put a negative b in the front. Negative 1 squared is 1 plus 4 is 5, so this would be a negative 5. So we got a negative 5b. Or plugging in a positive 1, thank you. So is that a positive 5 then?
Yes.
Yep. Thought we were plugging in a negative 5. Oh, negative 1. Positive 1. All right, so then b equals, looks like a negative 2. So we got 2 of them, that's good. Now the cx plus d part's kind of tough, I think. because there's nothing really to plug in here. There's nothing to plug in to make this happy, to make this work. Because there's nothing that's going to make other stuff go away. There's nothing that's going to make this 0 unless you go imaginary. And that would kick both those terms out. It might help us, but it's going to be a bear. So what we have to do on this one is plug in a couple values and try to solve for C and D separately. So let's go ahead and plug in a different value. Like let's say we plugged in x equals -1 for this one. That'd be the next, probably easiest one to plug in. So throw on a -1. See what we get. I think that's right. Double check me as I go.
We're plugging in a -1?
Plug in a -1.
Okay.
Yep.
Wait, that's the one.
Double check me as I keep going.
You got it.
Okay.
Okay.
Why would that be a -5?
Because it's 5 times -1.
Oh, Jackson.
-1 squared is 1 equals 5 times -1
Oh.
is -2.
But it's like a -1 times -2 times +5.
Oh, you're right.
So it's -10.
-1 times -2 is 2.
Oh, jeez. Okay, the numbers and letters and X's. I give up.
The easiest.
Oh, don't give up.
Algebra was a few years ago.
Don't give up yet.
Is linear algebra in college, is that hard?
Super.
Super hard?
Is that like the hardest one?
Going pretty good.
What is linear?
What's hard about it?
Just open up the page and find a math problem. Just enjoy. Alright, so now plug in x equals 2. The problem here is I've got 2 variables still, so now I got to pick a different x value. I just picked x equals 2. Plug in an x equals 2 and see if you can get a second equation with d's and c's in it, and then we could just use a quick substitution elimination or whatnot to solve for C.
Wait, X equals 2 is the original?
X equals 2 into this original one again to get a second equation with d and c. I know, I told you, they're a little mean on this one.
What
But,
the heck?
Why did you pick 1 and 2?
arbitrary.
Very easy.
1 I picked because it makes that 0 and makes that 0. -1 completely arbitrary. 2 completely
So
arbitrary.
if you want to, you can pick 100.
You can pick 100. Yep.
Then you're going to get A's and B's, A and C's and D's. No.
No, because you already have the values of A and B from earlier. So you're still going to get values there. So. Anyways, so we get x equals 2. Let's plug in x equals 2 real quick, and then we should be good. Oh, we got plenty of time to do this. All right, let's see what we get.
0 equals.
That's nice.
I like the 0.
I heard it's a really long route. Yes. That's worse than it is.
For the first equation, could you factor the 2's out and divide them on the other side?
Oh, you can just take a 2 out of all of them.
Yes, okay.
Yeah, so 2 would equal d minus c. Perfect. We might actually do it on this one as well. It actually is not. It's going to be a push. Yeah, you can take a 2 out of all of those, actually. But you'll notice it won't matter when we're all said and done. I think my numbers are right here. I think.
Yeah, you're right.
Looks right. And then you get 4 equals 2D.
You might. If you eliminate it, you just left it in 2D. Because you have to divide by.
Wait, wouldn't 4 equal D minus A?
Use elimination.
Oh yeah, I was just going to subtract those.
Oh.
So I just get 12 equals nothing. 6 C, so C would equal 2.
And then D equals 4. And then you get 4.
Sounds right.
Now I got
And now you get integrated. Yep, exactly. They're all natural log integrations on this one though, which is nice.
Could you get the 2Ds by themselves and just set equations below there?
Substitution, I like it. Good stuff. Perfect.
Here's just like 2 problems. That's not.
Holy cow.